as we talked about before, if we had two systems where one system was at a high temperature and then the other system was at a colder temperature, so T cold, what we have then is a flow of energy from the hot system to the cold system, which is what we call heat. So again, heat is what we call Q. So this is an energy, so typically Q has units of joules, but it can also have other units. Other units for this can actually become a calorie, or what's known as a kilocalorie, where a kilocalorie is usually defined as a capital C-A-L. So these are typical types of units that we're going to see for heat. These are all just simply related to each other by multiplicative constants. So it turns out that there's an easy way to basically transfer between these two. I don't focus too much on that, but again, what's happening is whenever I have a hot system and I have a cold system, energy then is transferred from the hot system to the cold system under heat until eventually these two systems will equilibrate. So this will end up at a final temperature, this will end up at a final temperature, at which point heat then ceases to flow from the hot system to the cold system because they're at the same temperature. Now, when heat is flowing, what is then changing? So we want to know what's changing in this system and what is changing in this system. Well, ultimately, what's going to change is actually going to be dependent on the specifics of that particular scenario. But ultimately, what ends up changing is this quantity, which is called internal energy. So internal energy, we're going to call E sub internal energy. So what is internal energy? Well, internal energy has to do with the microscopic particles that are inside of the system itself. So this has to do with the microscopic constituents within the system. So what does that mean? So that means that the internal energy then is either going to be some sort of kinetic energy having to do with the fact that, again, in a solid, we know that the atoms are actually simply vibrating about some fixed distance away from each other. In a liquid, they're moving in all kinds of different directions, right? And a gas, they're also randomly moving in different directions. So whether it's a solid or a fluid, we know that the molecules, or the atoms or the particles which are on the inside, are always constantly moving. So that means that they can have some sort of kinetic energy. Now, typically, this kinetic energy, we're going to have basically three different types of actually kinetic energy. The first type is that usual translational kinetic energy. So in this case, the molecules are just moving in some particular direction with some velocity v, with some mass m. So this is going to have a translational kinetic energy, which is then equal to the 1/2 mv squared. This can be the rotational kinetic energy that we saw on the last exam. So in this case, we can have an object which is actually rotating. So let's say in this case, here's our molecule, which is then rotating with some angular velocity. So in this case, it's going to have a rotational kinetic energy, which is 1/2 the moment of inertia times the angular velocity squared. Or if you want to think, you could have something more like a dumbbell type situation where this is rotating about this center axis. So these two are rotating with angular velocity omega. There's another type of kinetic energy that it can have, which is known as vibrational kinetic energy. So in this case, again, if I have this dumbbell type thing, what will happen then is that these guys are going to be vibrating, so basically oscillating in towards each other. So this is all part of vibrational, so this has to do usually with some sort of oscillations about some sort of, again, equilibrium type positions. Now, notice that the particle can be doing all three of these, right? It can be moving with translational kinetic energy while rotating with rotational kinetic energy and vibrating. So it's actually moving and twisting and rotating and doing all kinds of fun stuff. So it can have a combination of all three of these kinetic energies. And finally, it can have some sort of potential energy, where that potential energy is usually going to be determined by what type of interaction is actually happening. So is it a chemical interaction? Is it a gravitational interaction? Is it electromagnetic? Is it nuclear? Is it atomic? So each one of these gives some sort of different type of potential energy associated with the fact that we have some sort of conservative force. So again, this potential can be chemical, nuclear, atomic, gravitational, electromagnetic, etc. So anything that is a conservative force gives us some sort of potential energy. So when we talk about an internal energy, what we're really talking about then again is the microscopic constituents, so basically the molecules or the particles or the atoms or whatever is on the inside, their energy as a sum total. So again, some sort of kinetic energy, which could be one of these three, or potential energy, or again, ultimately all four of these things basically together. Now, what does that mean? So that means if I was holding this cup of water, I'm talking about, in this case, the energy associated with these guys as they are moving on the inside and the interaction that the particles have with each other. Now, that does not mean that internal energy then has anything to do with if I move my cup from one side to the other side. So in this case, even though I'm giving the whole entire system a kinetic energy because I'm moving it, but that kinetic energy is not part of internal energy, that's an external energy, which is added on top of the entire system. So when I'm talking about an internal energy, I'm not talking about that. And I'm also not talking about the fact that initially, say my cup is up here, where this has a gravitational potential energy due to the fact that it's lifted above the ground. Again, it's not talking about that. It's simply talking about the potential energy from the inner particle interactions, which are actually happening inside of the system itself. So again, whether it's a solid or a fluid, there's some sort of interactions going on between these guys. So again, this is what we call internal energy. So again, internal energy is talking only about the constituents in the system, again, a solid or a fluid, and the types of energies that these guys actually have. Now, so what does that mean? So that means when I have heat flowing from a hot system to a cold system, we then have a change typically in the internal energy. So, now, the way this is going to work is one of typically two ways. Now, those two ways it's going to work is, let's draw a picture. So, when I have heat flowing into my system, that's either going to affect the temperature or it's not going to affect the temperature. So if we're away from what's known as a phase transition, what will happen then is what? If I plot the temperature, say, on this scale, or at least the change in temperature, versus the heat flow in this situation, if I'm away from what's called a phase transition, what will happen then is that there turns out to be a linear relationship between the heat and the temperature, meaning as energy goes into the system, that then increases the temperature of the system. Until we reach the point where we have what's called a phase transition, at which point heat flows into the system, but there is no change in temperature. Once I undergo a full phase transition, what will happen in that case then is I go back to being a linear relationship then between the heat and the change in temperature. So this point here marks the beginning. So this is the beginning of the phase transition. The beginning. And this is then the end of the phase transition. Where, again, this purple part is where the phase transition is occurring. So phase transition. So what's the difference between these? Well, the difference between these has to do with what is changing internal energy-wise. So typically what's happening is what? When I have these areas here, the green and the orange one, what's happening here is we're changing the kinetic energy. So here the kinetic energy is changing, and we know that's because, remember what we did in the last section, under that kinetic theory, temperature is related specifically to the average kinetic energy. So as heat is flowing from my one system into the other system, to have a change in temperature, I have to then be changing the kinetic energy. So meaning that if I was talking about a solid, these guys go from oscillating maybe like this to now oscillating much faster as the temperature is now increasing. Their average kinetic energy is now massively increasing. So that's happening both here and here. Right? Now, this stage where I now simply have a phase transition. What's happening during the phase transition then is what? I'm not changing the kinetic energy. What I am changing is now the potential energy. So typically what happens is during these two phases, potential energy doesn't actually really change. So the intermolecular interactions between the two under that original interaction, that original conservative force, doesn't really change much. The only thing that's really changing then is the kinetic energy. But here under the phase transition, what's happening is now I'm not changing my kinetic energy anymore, but I'm actually changing the potential energy. So what's happening here is I have to dump a lot of energy into the system to basically change that potential energy. So as an example, let's say I want to go from a solid to a liquid. So as we talked about under states of matter, what we know is that for a solid, this is usually something generated from some sort of lattice. So here is my lattice system, which has very large nearest neighbor attractions. Right? So this is my solid. But to go from the solid down to a liquid, again, a liquid is they have large-ish interactions, right? Nearest neighbor interactions. But now I'm no longer on a strict lattice. I'm now just in a big cluster. These guys like to cluster on top of each other. They still have strong interactions, but nothing is near as strong as the rigid lattice that this guy is set up on. So what happens then is what? These guys will basically oscillate at exactly the same rate. So the kinetic energy doesn't actually change, hence the temperature doesn't change. But now I have to put a lot of energy into breaking these nearest neighbor attractions, these very strong nearest neighbor attractions, to bring them down then into a still strong nearest neighbor attraction, but not on a strict lattice. And it takes a lot of energy for me to actually do that. So during the phase transition, what we're actually doing is we're breaking these nearest neighbor attractions. And it's the same thing when I try to go from liquid to a gas, because when I go from a liquid, these guys are tightly packed. There's a lot of, again, strong nearest neighbor attractions. But then when I go to a gas, these guys are now really far spread out. The only thing that's usually interacting between them is gravity, or at least electromagnetic, something like that. But these are long-range forces causing these guys to, again, barely move around each other. So again, it takes a lot of energy for me to actually break these. So that's what's happening during these phase transitions. So during this portion here, during the kinetic energy is changing, what we know in this case then again is that the heat is going to be proportional to then the change in temperature. During the phase transition, in this case, we know then is that the heat is no longer proportional to the change in temperature because there is no change in temperature. So these two things are going to have to be described differently depending on what is actually happening. So am I changing the kinetic energy, i.e. am I away from a phase transition, or do I have a phase transition occurring? So how do we describe each one of these? So this one I'm just going to jump directly into specific heat. So here, away from a phase transition, what happens then is that the heat is then equal to the mass, so this is the mass of the substance, times what's known as the specific heat, times then the change in temperature. So this is the relationship then between the heat and the change in temperature for when I'm away from some sort of phase transition. So again, M here is simply the mass of the substance. So for example, if I'm increasing the temperature of ice from minus 10 degrees Celsius to minus 5 degrees Celsius, then this is simply the mass of the ice. Specific heat is a property or material dependent property. This is material dependent. So basically meaning that it's a constant, but that constant is different for all different substances. And not only is it different for all different substances, but it's different for all different phases of that substance. So for example, water, there's a different specific heat for ice, a different specific heat for water, a different specific heat for vapor. All of them have their own different specific heats because the amount of energy at which this thing takes to change by a single degree is different for all of these different types of phases. And then change in temperature here, this thing is, depending on what units I'm working in, this is either going to be, either in degrees Celsius or in Kelvin. Just depends on what it is I'm working on. Now, what this means is since this has units of joules, this has to have units of joules as well, but this has units of kilograms, this has units of temperature. So that means C then, specific heat, has units of joules per kilogram per either degree Celsius or joules per kilogram per Kelvin. So this is specific heat. Now, what happens then if I add different systems together? So let's say I have all kinds of different stuff put together. So let's do an easy example first. So let's say I have water at some cold temperature, and then let's say I heat up a piece of aluminum. So here's my aluminum, so that this thing has some hot temperature of TH. So basically what happens here is what? Since the aluminum is at hot temperature, the water is at a cold temperature, what will happen then is I'm going to get heat flowing from the aluminum into the water. Right? Which basically means that what? This guy is going to have a negative change in temperature, which means that he's going to have a negative heat. Right? Heat is flowing out of the system. Simultaneously, the water is going to absorb that heat, which is flowing out from the aluminum. It's now going to absorb it into the water, which means his temperature is going to increase, which means he has a positive change in temperature, which means then he has a positive heat flow. Now, what we're going to do is we're going to pretend that this system is what's known as thermally isolated, meaning that all the heat flow is only going to flow within inside of the system itself. So let's say this is thermally isolated. So in this case, what that means then is all the heat which flows from the aluminum, that negative heat, the flowing out, is going to flow into the water, so that's going to be a positive. So the sum of those two things is simply going to be equal to 0. What happens now if I add a third thing in here? So now let's say we add a third thing. So let's say now I put a piece of ice in here. So this is T hot, this is T cold, but this one is now going to be T super cold. Let's call that super cold, right? So this guy is simply going to have a colder temperature than this guy. So what will happen in this case then is basically the same thing. So I'm going to have heat flowing out of the aluminum into the water, but it's also going to have heat flowing out of the aluminum directly into the ice, right? So I get some heat flowing here, I get some heat flowing here. So as the water, though, is increasing its temperature, it's at a higher temperature than the aluminum, the ice, which means that some of his heat also is going to go directly into the ice. Right? So basically what will happen is some of the heat that's flowing off from the aluminum will go into the ice, or into the water as well as into the ice. But since the water, again, is at a higher temperature than that of the ice, some of his heat will also flow into the ice. So the ice is going to gain heat from both the water and from the aluminum, but the water is going to gain heat from the aluminum. So basically this one's going to divert his heat into different directions, where this one is going to have directly all of his heat sent into the ice, until eventually what will happen is what? This whole entire system will again equalize. Now here, if we assume that the ice doesn't melt, what will happen then is that what? The temperature of him will drop, temperature of him will drop, until this becomes some sort of below 0 degrees Celsius to ensure that this guy doesn't actually melt. Now what will happen then, again, is that he will end up having a negative temperature change, because his final temperature will be less than the initial temperature. The water, even though the water is gaining temperature or gaining energy from the aluminum, overall his energy is going to end up being diverted into the ice, which means he will also have a negative change in temperature. So his Q will be negative, his Q will be negative, because they're both going out from the systems, where his Q ends up being positive. So again, if I add the heat from then the ice, plus the heat from the water, plus the heat from the aluminum, This will be positive, negative, and negative, so I get plus, minus, minus, which ends up giving me 0. So ultimately what ends up happening then is for a thermally isolated system, no matter how much heat everybody is giving up, the total heat of the entire system must be equal to 0. This is what's known as calorimetry. So calorimetry says is that the net heat is equal to 0, which is then equal to the sum over all possible heats. Now again, some of these will be positive, some of them would be negative. We don't insert that negative sign in there. The negative sign will come from the fact that the change is negative. Okay? So this is then simply equal to the heat from 1 plus the heat from 2 plus the heat from 3 plus the heat from blah, blah, blah. Okay? So here, as long as my system is thermally isolated, which as far as this class is concerned, that will always be true, then the total net heat of the system will be equal to 0. So again, some of these are going to be negative because they're going to lose. For example, this might be heat of the aluminum plus heat of the water plus the heat of the ice. This will be negative, negative, and positive, such that the entire heat flowing is 0. The only time this thing would be non-zero is if I was losing heat to the exterior, meaning it was not thermally isolated, or if I had heat coming in from the exterior. If I was losing heat to the exterior, that would be a negative. If I had heat coming in from the exterior, that would then be a positive. So this would not be 0 in this case. But as long as I have thermally isolated, what has to be true is that that total heat then must be equal to 0. Okay? This is what's called calorimetry. Now, what happens if I do have a phase transition? Well, if we do have a phase transition, so in this case, again, the heat flow is no longer proportional to the change in temperature. This is not true anymore. So specific heat doesn't apply anymore. So basically we have to come up with something else. That something else is what's called latent heat. So latent heat is the heat while this thing is undergoing the phase transition, meaning while the potential energy is changing, not when the kinetic energy is changing. So in this case, this is now going to be equal to plus or minus the mass of the substance. So again, this is of the substance times what's known as the latent heat. So L here is simply called the latent heat. Now, latent heat, again, is going to now be dependent not only on the type of material, not only on the phase of the material, but also if it is condensing or melting or vaporizing or etc. So here it's going to depend on what phase is it going from to. Now here, the plus and minus is inserted because this is always a positive quantity. This is also a positive quantity. So the plus and minus is here to make sure that we get right if the energy is being absorbed or if it's being emitted or released. So if the energy is being absorbed, we use the plus sign. So this is then absorbed. So that means I have energy going into my system, and then a minus sign is if this is being released. So energy is flowing out of our system. So the types, in general then, we have 3 different types of latent heats. So the first type is what's known as sublimation. Is that right? So let's see. So the 3 types. So we have the latent heat of vaporization. Write that one down. Vaporization. The latent heat of sublimation. And what's the first one again? My brain is melting. Alright, let's see here. Oh. Fusion. That's what it is. There we go. It wasn't sublimation. Okay. Good. So let's talk about each one of these. Fried my brain. Okay. So anyways, latent heat of fusion. So what is latent heat of fusion? So latent heat of fusion is either when we go from a solid to a liquid or from a liquid to a solid. This is the latent heat of fusion. Now, in this case, when it goes from a solid to a liquid, energy is being absorbed because I have to take in energy to break those nearest neighbor bonds. So in that case, the upper arrow here corresponds to the positive sign. Where if I go from a liquid to a solid, I used orange in that case, that's now going to be a negative. Right? So that's what we call latent heat of fusion. Latent heat of vaporization is when we go from a liquid to a gas, or from a gas to a liquid. So again, the way we read this is when I go from a liquid to a gas, it has to absorb energy. Again, I have to break those nearest neighbor attractions to get them to fly away from each other. If I go from a gas to a liquid, when I condense it, I have to release energy for it to cool down enough to be able to condense it. And then finally, sublimation is when we go directly from a solid to a gas, or from a gas to a solid. So this is what we call sublimation. A good example of this would be something like dry ice, right? So dry ice, you throw it down. In that case, it doesn't actually turn into liquid. It actually goes directly into a gas. It's a good way to make fog, right? So if you don't have enough money to actually buy a fog machine, just buy some dry ice and throw it out, and then that'll basically start evaporating and then turning into gas directly, which kind of gives you that smoky effect. So if you ever want to make a movie, just buy some dry ice, and it's the easiest way to do it. So anyways, good. So as far as our class is concerned, we don't necessarily care about sublimation. All ways we're going to do this then are either fusion or vaporization. So it's going to go directly from a solid to a liquid, or from a liquid to a gas, or vice versa. Now what happens here? So let's go back to a simple example and talk about how this one works. So let's say now I'm going to put ice into water. So again, here's my water, which is going to act as my T-hot. And now I'm going to put a chunk of ice in here, where my chunk of ice is going to be T-cold. Okay, so it's going to be T-cold. So, again, what's going to happen is I'm going to have heat flow from my hot system into my cold system. So that means it's going to go from the water into the ice. So this is my heat. But let's say that I have a sufficiently high enough temperature of water, or at least I have enough water, such that I'm going to completely melt the ice. So, what happens? So in this case, again, if I have a thermally isolated system, basically the same thing is going to happen. I still have that calorimetry. I still have to have that the total net heat must be equal to 0. So I still have calorimetry. But basically what's going to happen here, though, is I'm going to end up then with the heat of the water. Right? This is going to be my heat of the water. But for the ice, I have to be careful. Because the ice, what I have to do first is I have to bring it from its initial temperature to 0. Then from 0, I have to melt it. Then I have to take that amount of mass of ice, which is still the same amount of mass, but now it's a different substance, and now I have to bring that to the final temperature. So for the Q of ice is actually going to split into 3 pieces then. So Q of ice then, I don't know why I put a C on there, but ice, there we go. So Q of ice then is going to be equal to the Q from whatever the initial temperature is, the initial to 0 degrees, plus the latent heat of fusion, because now I have to melt it, plus Q from 0 degrees to whatever that final temperature is going to become. So anytime I have a phase transition, each time I have a phase transition, that simple 1 Q breaks up into 3 Qs. So I have to bring it from its initial temperature to its final, to the temperature at which it has to go under the phase transition, which is either going to be 0 degrees for water or 100 degrees if I'm going to vaporize it. So I have to bring it from that initial temperature to there. Then I have to melt it or vaporize it. And then I have to increase its temperature from either 0 degrees or 100 degrees, depending on which thing that I did, up to its final equilibrium type temperature. So this means that whenever I have a phase transition, my total then is going to be, again, Q of water, since that is not changing, but then plus Q from the initial temperature to 0, plus Q of the latent heat, plus then Q of 0 to the final temperature. Now, for all three of these, the mass stays the same. So this is simply going to be the mass of the ice. So even when I melt the ice, I still have the same amount of mass at which I melted the ice. But what's going to be different here is that here, this is going to be C of ice, right? Because this is going to have the specific heat of ice. But then here, I've now melted it, so this is now going to be the specific heat of water. So even though the mass stays the same for all three of these different pieces, what's different now is that the specific heats are now different because now I have different substances. And then again, if I added something else in here, like aluminum, so if I put an aluminum piece in here, then I would just add on the Q of aluminum as well, and then add on many other Qs, so that the total net Q must be equal to 0. Again, simply calorimetry. Calorimetry stays exactly the same. The only thing that's different now is whatever it is that I am freezing, turning into a solid, or melting, turning into a liquid, or vaporizing, or condensing, that Q has to be split up into 3 pieces. That's the only change. Everything else actually stays exactly the same. So, good. So these are what happens then when heat flows into the system. So again, what I'm changing is the internal energy. So that microscopic energy has a change in the inside. For something like the water here, in this case, I'm changing its kinetic energy because all I'm doing is I'm changing its temperature, which is what we call specific heat. For the ice here, since I'm melting the ice, I'm going through a phase transition. So first I'm increasing its kinetic energy. Then I'm increasing changing its potential energy. That's where most of the heat is going to go. And then finally, I'm going to, again, increase its temperature. So I'm going to increase its kinetic energy again. So ultimately, all of that changes the internal energy of each one of these substances, in this case, these 2 substances, by causing this one to have its kinetic energy decrease, this one having its kinetic energy increase, changing its potential energy, and then increasing its kinetic energy again. So, this is what the heat does to our system. So in the next video, we'll do a couple examples. So first we'll do one without a phase transition, and then we'll do one with a phase transition, just so we can see the difference between each one.